Thanks a lot for the introduction. So yeah, that's true. Let's say this presentation will be engineering oriented and maybe not so much theory. And we start when proof of principle experiments are already done and technology is mature enough to make a product. So topic of my talk today will be optical frequency combs and lasers for industry. And as a subtitle is OptiClock, iqClock and Action, European Union Quantum Flagship Projects. And this is also outline of my talk today. In the very beginning, just one remark. Many of the slides originate from our company presentations, but please consider this as a general tutorial because physics is the same for many types of combs and the same parameters or the same characterization methods. So the slides that I will show you, they are not only limited to the frequency combs of TOPTICA. Just very briefly, who we are. So we are TOPTICA Photonics Group. We are located in Munich, in the south of Germany. Currently, we have something like 300 employees, 230 of them in Munich. And our revenue is around 65 million euros, and we were grounded in 1998, so 21 years ago. The technologies that we cover are laser diodes, ultra-fast lasers, including frequency combs, some terahertz generation, spectrometers, and high-power laser diodes. And the group consists of TOPTICA Photonics in Munich, but we have also some production and R&D in US. Eagle Yard Photonics is our daughter company in Berlin, producing laser diodes. And TOPTICA Projects is a daughter company for complicated and risky projects that do not fit into TOPTICA Photonics portfolio, like guide star lasers that we talked yesterday in the observatorium. And we have two daughter companies in Japan and China. Okay, that's it. So right now I will very briefly show you some basics of the frequency comb. Maybe it's obvious for you, but maybe for some of you can be useful. So first question would be motivation, why we are talking about frequency combs today, and what's the frequency comb at all? Why do we need them? So the short version is that frequency comb is a tool for precise measurement of optical frequencies. And with this tool, one can transfer stability of RF reference, like cesium clock, into optical frequencies, or other way around, transfer excellent stability of optical reference, like 1 Hz cavity, down to microwave or RF frequencies. And the key applications of the frequency combs are obvious. It's optical metrology to measure optical frequencies, very high resolution spectroscopy, stabilization of CW lasers to the comb. And what's more relevant in this community will be measurement and evaluation of optical atomic clocks, time and frequency transfer, and low noise microwave generations. So let's start from the beginning, and these are cavity modes. So if we have a laser resonator with laser medium, there are obviously some modes allowed inside of the cavity, and the longer cavity is, then we have the smaller spacing between the frequencies. And in a regular laser diode, multi-mode laser diodes, the modes are out of phase. So phase relation is random, it's not fixed. And the consequence is that output intensity is continuous wave. So this is continuous wave operation, like from this laser pointer. On the other hand, if all of the modes are synchronized, then the output is a pulse operation. And the more modes, the shorter pulses out of the cavity. And if we have a very close look at the pulses from the femtosecond laser source, one will discover that the electric field inside of the pulse is not constant. And from pulse to pulse, there is a small shift in a carrier envelope phase. And this is called carrier envelope offset. And the pulses are separated by delta t. So this is inverse of the repetition rate. And when one looks close over spectra of a femtosecond laser, on the optical spectrum analyzer, it's a very broad spectrum. But while looking very closely with very precise equipment, one can discover that actually spectrum is not continuous. There are modes. And all of the modes are separated by the repetition rate. And the number, also the frequency of node is obviously harmonics of the repetition rate. But there is also one factor that is offset frequency of carrier envelope offset. And the reason is this phase slip between the pulses. So phase and group velocity inside the cavity is not equal, and that is why there is that shift, which means that the pulses start with some offset frequency FCO. Okay. So let's have a look again at the regular femtosecond laser. And regular femtosecond laser that we have already since maybe 30, 40 years on the market. They had no stabilization of carrier envelope offset frequency. That means that this offset frequency was jittering or drifting over the time. And the result is that all the comp lines in optical domain also are drifting and are not stable and not stable enough for optical metrology. And the second thing is that free-running laser without any stabilization of the repetition rate, then obviously repetition rate is changing over the time, and the mode spacing inside of the optical spectrum is also changing, and the modes are briefing. So this is a difference between regular femtosecond laser and the frequency comp, is that both carrier envelope offset frequency and the repetition rate are stabilized to a very precise reference. So just as a short summary, frequency comp is a laser. So it's a laser with spectrum consisting of a series of discrete equally spaced lines separated by repetition rate. It's a frequency ruler, so the spacing of the mode is equal. And there is fixed phase relation between the lines, and there is direct link between repetition rate or radio frequencies and optical domain. Okay, so how frequency comp is used for optical frequencies metrology? So this is a principle of heterodyne bit detection. So a part of the laser that has to be measured has to be mixed together with a frequency comp light, and usually it takes place in a bit detection unit or beam combiner. It could be beam splitter, or it could be fiber coupled version like here. Then this frequency comp line and laser line has to be filtered, because usually frequency comp spectra is very broad, but we are interested only in a bit frequency between one comp line and continuous wave laser. And all other remaining laser lines just make an offset on a detector that we don't want to have. So usually this part, like filtering and a detector, photodiode, is just in a bit detection unit, or in our case it's called monochromatic detector. And the output of the detector can be observed on the RF spectrum analyzer. And what actually happens there is just beating of two continuous wave lines, and one get two factors. So one is just frequency difference on the photodiode, and the second sum of both of those two frequencies is just too high for a photodiode and will not be observed. And for the metrology, the signal is usually counted by a dead time-free counter. In the frequency domain, it's a very similar picture. So we have comp lines with a position FCO plus mode number times repetition rate. And there is a laser line that there is a beat, which is marked here offset, RF offset frequency. And the frequency of this laser is just frequency of the comp line plus minus offset frequency. The signal that can be seen on the photodiode is just radio frequency comp. So this is just repetition rate and its harmonics, and obviously a bit signal. And what's very special about frequency comp is like really precise measurement. And here we can see, very first comp measurement of ytterbium clock transition made at the PTB, at the Harald Steller group in the year 2001. And so the black part of this whiteboard, that was known ytterbium frequency until the time of experiment. And this experiment with a frequency comp just improved the precision by 7 digits. So this type of experiment or invention of frequency comp was so important that the Nobel Prize was given in 2005 for that. What one can see on the spectrum analyzer is just a bit frequency and repetition rates, and there are mirror images around every repetition rate peak. Usually the mode number can be measured by wave meter or by a frequency comp itself when changing repetition rate. Okay, so the question could be why these measurements were possible only at the end of 90s or around year 2000 and not already 40 years ago. And the problem was to measure and to stabilize this offset frequency. So carrier offset frequency, I already briefly explained what's that. And right now I will explain how this offset frequency is measured and stabilized. So so very important point is to have an octave spanning supercontinuum. So a spectrum out of the oscillator that the highest frequency is at least twice higher as the lowest frequency inside of the spectrum. And till late 90s, there were simply no such, there was no method in order to get such a super continuum. So the proper photonic crystal fibers or nonlinear fibers were missing. And as soon as one gets an octave spanning spectrum, then one can simply take, okay, this is frequency axis. So this part is a red light with lower frequency, and this part is a blue with higher frequencies. So the idea is just F to F interferometer. So to take that lower frequency part of the spectrum, frequency double it, and mix together with the high frequency components of the spectrum. Mix both of them together, beat on the photodiode, and just when we look at the equations, twice the frequency of lower part, so there will be 2 FCO plus 2 harmonics of the repetition rate, and when one divides from the blue part of the spectrum, twice harmonics of the repetition rate plus FCO, the product is just FCO, carrier frequency offset frequency. So signal from a photodiode, there is one can measure it. It can be it can go to the feedback loop and be stabilized in the oscillator. So this technology works very well. It is, let's say, standard on the market, but has several disadvantages. First, it requires a feedback loop. So there is an extra feedback loop in the system. So the bandwidth of the lock is limited. One needs extra actuator in the oscillator, and very often carrier envelope offset frequency and repetition rate are not orthogonal. So changing repetition rate can change carrier envelope offset.
Can I ask you a question?
Yes, sure.
I was wondering what is actually changed to stabilize the carrier offset, like in the typical.
Yeah. So there are. Yeah. So there are different. So very obvious is, for example, piezo, just to change the cavity length, to change the temperature. In case of fiber lasers, one can change a pump current. So pump current will be a small stroke, but with very high bandwidth. One can use a modulator inside of the cavity. So these are the most typical.
If you change the cavity length, you also are changing the repetition time. So how do you?
Yeah, so that is why I just said I want to point here that these two parameters are sometimes not orthogonal, and it's a kind of trouble to independently change carrier envelope offset and repetition rate. So one can deal with that. One need.
That's my question. How do you deal with that? To do that in a reasonable way, conventionally.
Historically, there is, for example, one can take two prisms, so prism pair, of two different type of glass material, and just put them together. So here will be, let's say, dispersion number 1, and here dispersion number 2. But the total thickness of the glass block will be the same. So just by shifting the glass block, one can change dispersion inside of the resonator, but affect a little bit on the repetition rate. This is not very fast mechanism, but was already done very often in the past. Different way is just to use a pump current of a diode to change FCO, because there will be bigger effect. While changing pump current of a diode, there will be a different energy inside of the oscillator, and it affects FCO much more than repetition rate. And of course, just using EOM modulator inside of the cavity is what can be done nowadays. Yeah. But it's a kind of problem because it just requires extra actuator and extra control loop. But one can deal with it. And one issue that may be there, that there is additional photodiode needed in order to measure offset frequency. So that could be some amplitude to phase noise conversion. That could be an issue with a very high precision metrology. And what we do is a little bit different. This is offset-free comp by means of difference frequency generation. So the idea is as following. Also, the core component is the same or similar fiber laser oscillator with actuators. Like, okay, I don't know why it's cut, but there should be a temperature, piezo, and pump current. And just part of the light is sent back to the repetition rate stabilization unit. And the main output of the fiber is sent to the amplifier to boost up the power to some several hundreds of milliwatts and to generate super continuum, very similar, like in the case of conventional comp. But what's special right now is that the super continuum is a little bit broader than conventional F2F interferometry. So the short wavelength part has to be around 850 nanometers and the longer part around 1860 nanometers. And in this case, just superposition of those two parts of the spectra on the nonlinear crystal generates a difference frequency comp without any offset frequency. And these values, 850, 1860 nanometers or around, just gives a difference frequency around 1.5 micron. So the resulting frequency comp is compatible with the standard telecom components and the original comp out of the erbium doped fiber laser. So the result is reduced frequency comp equation. So all the comp lines are just a harmonics of a repetition rate. FCO is fixed to 0, and offset frequency and repetition rate are completely decoupled, that I will show right now.
Sorry, I have a question. Could you go back? So why these two frequencies? I mean,
so no, this is a broader band. So this is not a very one fixed frequency. So output of the DFG comp is also something like, around 30 nanometers broad. So of course this is, so if you do the math and you just calculate the energy of this part of the spectra and this part of the spectra and you subtract both of them, then you will end up around 1.5 micron. But this is not very particular single frequency. This is, broad spectra. Did I answer your question? Or you could choose a little bit different ones, but this is a trade-off that it has to be around 1.5 micron, and it has to be available out of the highly nonlinear fiber. But it's not that this is only this frequency gives you 1.5 micron output. I will show you it in a following slide. So, so basically, we should look at the formula. So this part of the spectra has a m mode number. So m times repetition rate plus FCO. This part of the spectra has n times repetition rate plus FCO. And when you subtract both of them, then you end up with m minus n times rep rate. Because here is FCO component, here is FCO component. And if you subtract both of them, it just disappears. But I will show on the next slide. here is what happens. So let's assume that there is a pulse with a phase at 0. We generate supercontinuum. Both of the components, the red one and the blue one, they share the same FCO. We subtract the lower frequency part from the higher one, end up at 1.5 without an FCO, and this is the result of a new pulse. So phase is constant. Then the next pulse, okay, the phase is shifted by the offset frequency. You generate again the broad spectra, short wavelength components and long wavelength components. They share the same FCO. This is a different FCO than in the previous pulse, but it doesn't matter because we subtract one from the other one and we end up with FCO 0. So the result is just a pulse with a 0 offset. And one can continue it all the time. So the phase relation is always constant and FCO is equal to 0. So we believe that there are advantages of this approach. So DFG, difference frequency generation, is taken from each pulse individually, and this process is just all optical process by optical means. So there is no electronics, there is no control loop with limited feedback. It's 2 orders of magnitude faster than typical electronics bandwidth. It happens with speed of light. No, it happens with it happens in the optical domain. So we believe that it's simple and more reliable. That we'll show also later. And right now, let's think. Okay, so the phase relation between the pulses is constant, but what about phase noise? And one can measure it. So the method of measuring phase noise of carrier envelope phase is, for example, spectral interferometry. So the setup is very similar to F2F interferometer. Just take an output of the frequency comp, generate supercontinuum to have frequency components, like let's say around 1 micron and 2 micron. Frequency double the long wavelength part, and that bit both of the signal, but then do not measure a bit frequency, but send the signal to the spectrometer. And if both of the pulses overlap, then we'll see interference fringes. And the spacing between the fringes, it's just a position of a delay line. So the closer the pulses are, the less fringes are on the spectrum analyzer. And the absolute position of the fringe, this is the phase noise. So if the phase noise is not stable, then those fringes will just drift back and forth in every direction. So here you can see the output signal of the optical spectrum analyzer, and you can see very straight lines. And this is just integrated phase noise. So this method was described very well in optics letters of Krauss in the year 2011. One could say, okay, that is very fine. We've seen the stability on the long term, because spectrum analyzer is just a slow device, so there are maybe just several measurements per second. So there is also a different method, or maybe an upgrade to the previous one. And instead of taking a spectrum analyzer, let's just use a bandpass and short and long pass to isolate just 2 peaks. And let's illuminate a balanced photodiode with that short wavelength part and long wavelength part. And then any fluctuation in a peak of the fringe position will be measured by a balanced photodiode, and after some math gives us a result of phase noise. And here is an example of the phase noise measurement from the setup presented by Lille et al., group of constant, 2 years ago. So here we can see the high frequency components and this phase noise characteristic and integrated phase noise value in the blue. So phase noise of such a DFG comp is like 33 milliradian between 100 hertz and 2 megahertz. So this frequency range is very typical on a data sheet of many providers of frequency comps. But with this method, we are not limited by the electronics, by the bandwidth, so we can measure also in a different frequency range. So down to 70 millihertz, we have only 33 millirad. When we measure the frequencies up to 20 megahertz, it's 61, or half of a rep rate is 135 milliradian. And the answer of other manufacturers could be, okay, we measure just only up to 2 megahertz because there is anyway no effect in the higher frequencies, but they do not show it, and we can show what happens here. And another property of the DFG comp is that fixed point of the noise after DFG process is at frequency of 0. So usually in oscillators, fixed point, so the frequency where there is the lowest phase noise is at the frequency where oscillator oscillates, so optical frequencies. After DFG process, this frequency is shifted to 0. And there is something like elastic tape model that describes the distribution of a phase noise. So the longer or the more far away one is from the fixed point, the higher phase noise is. And after DFG, this fixed point is shifted to 0. So one can see more or less here what happens. If there is some timing jitter, that blue frequency components suffer more than the red frequency components. So one can see it with a line of that red part is less long than the blue one. And we've checked that experimentally if this is the true. So we measured phase noise of the frequency comp with a Hini laser with cavities 1162 and 1.5 microns, and we can see that this measurement fits very well to the theory, and that gives potential of a very low noise microwave generation, because fixing that phase noise, so let's say locking to the optical cavity, like 1 Hertz laser, will just fix the noise at optical frequencies to the value of optical reference, and then this noise will be divided down to the microwave region. So potentially one can get a very low phase noise microwave. But so far we haven't checked it yet, only in the infrared and visible range. Here we can see the same how the phase noise scales. So this is phase noise measurement at different frequencies, and after scaling all of them, one can see that that phase noise at 1162, 1550, and 850 nanometers overlap perfectly. So let's say this is a textbook behavior. On this part of the slide, I would like to show you something very interesting. And this is phase noise of the oscillator when locked to the different references. So this line is more or less phase noise of a free-running oscillator, femtosecond laser. And if that oscillator was not locked to the RF reference, like cesium clock or hydrogen maser, then it will just continue and go up. And when locking to the RF reference, this is important to keep in mind that, okay, in lower frequency range, that RF reference will have better properties than free-running frequency comp, but there will be somewhere crossover frequency that free-running frequency comp or optical oscillator will be already more quiet than RF reference. So it is important to limit the locking bandwidth just to that crossover frequency. One could lock harder, but then frequency comp will be worse. And so that is what we can see here. In our case, RF reference is better than frequency comp up to around 10 to 15 kilohertz. And this is the corner frequency and the lock bandwidth of our control loop. So basically we could lock it tighter with higher bandwidth, but overall performance would be worse. The lower part of the graph is frequency comp locked to the 1 Hz laser at 1162. So one can see that the phase noise characteristic really drops down as expected from the optical reference. And then here one needs, okay, much higher bandwidth. But again, at some point, free-running oscillator will be already more quiet than 1 Hz laser. So it is not always good to have as high as bandwidth as possible. And one could carefully choose locking bandwidth. Right now, I would like to address line width of comp modes. So one cannot just tell what's the line width of the comp without considering what's the frequency range or the wavelength, because there is quadratic scaling of a phase noise. And in this case, we show a bit between frequency comp and some narrow line width source from NKT with a line width of 100 Hertz. So that is, let's say, much less than the line width of the free-running comp, and what we measure is a line width of something like 17.4 kilohertz at 1.5 micron. And when performing a similar measurement at 633 nanometer, then one can see a bit of 75 kilohertz. So there will be always quadratic scaling of the noise. The shorter wavelength, the broader line width is, unless one locks the laser to the optical reference. And then, of course, at this frequency, frequency comp will inherit the phase noise characteristic of the reference and can be as short as 1 Hertz, or as narrow as 1 Hertz. The next parameter of a frequency comp would be stability, or maybe one should say instability of the frequency comp. And these are measurements that were done in collaboration with PTB. So these were measurements at the PTB facility done by Eric Benkler, Berghard Lippard, and Uwe Ster. So what can we see here is just a frequency comp with an output with 1.5 micron and around 698 nanometer strontium wavelength. And in these measurements, was measured the frequency of strontium clock laser of PTB, strontium beast, and silicon cavity. And in order to perform comparison of clock, or in order to say what's the stability of clock, one need to have two clocks to compare. And the same is with stability of frequency comp. One need to have two frequency comps to compare the results. And in this case, we had one FCO free comp and one conventional frequency comp. And the results of the measurements were there as frequency ratios between the strontium and silicon cavity lines. And with every measurement, one need to make a very careful error budget and error considerations. What is the influence of the external parameters? And that is what Eric did. He just looked at what's the detection level of the system, what's the influence of the change of temperature and on the fiber, and fluctuations in air pressure, and he ended up with these results. So here we can see the time domain trace. So okay, unfortunately this y-axis is cut on the beamer, but here we can see a deviation from the mean frequency, and this is modified Allen deviation. And the value that we can see here, okay, it can be also seen here. So at 1 second, it is 10 to the 8 times 10 to the minus 18, and after averaging of 10,000 seconds, the modified Allen deviation value was 5 times 10 to the minus 21. This measurement was shows the most unstable comp in the system, and with our comp, this was the lowest value measured at the PTB at the time of experiment. And so there is also one aspect that needs to be considered when thinking about frequency comps in a very precise metrology with the highest precision of optical clocks, is the configuration of a frequency comp, and this is single versus multi-branch. So in the previous experiment, everything was true single branch. So 1.5 micron light and 698 light had the same optical path. In this configuration, the light out of the frequency comp is split into two. So let's say this part of the light for bit detection with PTB cavity is much shorter than this branch, having erbium doped amplifier, nonlinear fiber, frequency doubling stage, ending up at 698 nanometer. So this multi-branch configuration, we've tested at the PTB2, and Eric also made a very careful budget. What's the influence of instability in the system with multi-branch configuration, and we end up with these results. So we are here higher than detection limit, and here is also the comparison. So having a frequency comp with a true single branch configuration, this is the red line that I showed before, and uncompensated frequency comp with a multi-branch configuration for different lasers shows worse performance due to drifts in the laboratory, change in the air pressure, and so on. So even this value is pretty good, but in order to compare the best clocks in the world, one could think maybe about a single branch configuration. Okay, so the next topic will be, I will show you some insight of the frequency comp and talk about extensions. So this is actually a picture how a frequency comp looks like. So this is 19-inch broad sub-rack mount and 60 centimeter deep. And inside of the frequency comp, one can, usually this oscillator, amplifier, supercontinuum generation, difference frequency generation, some distribution amp with up to 8 outputs, lock-in electronics to stabilize the repetition rate, and embedded system, all the drivers. And there is also something like DFC Core Plus version that is very similar, but also supports optical lock to the cavity. And having even the best frequency comp at 1.5 micron is of no use if your clock transition is at 698. One need to transfer the wavelength. So I will show you the typical way how it's done. So here is an example. For example, a frequency comp for calcium experiment. One need 866, 850, 794, 729. In the case of strontium, 813, 689, 698. So the usual way of dealing with that problem is just adding an extra amplifier to 1.5 micron to boost up the power to the several hundred milliwatts. At the end of the amplifier stage, there is highly nonlinear fiber, and that shifts the wavelength, dispersive wave, towards shorter wavelengths. So here we can see example of tuning of the frequency shift just by changing pump current between 800 milliwatts and up to 1.1 micron. So one can see a very nice shift between something like 1400 down to 1050. When shorter wavelengths are needed, then one need to switch to a different type of nonlinear fiber, and one can cover the lower part between 1050 and 840 nanometers. And here we can see that this characteristic is it's very different. So tuning range is much more narrow than with in a infrared range. But anyway, with this type of nonlinear fiber, one can shift only up to 850 nanometer. And if you want to have a shorter wavelength, there is a solution. Oh, this is just an insight how such an extension looks like. So this is just erbium dot amplifier shining green with 980 nanometer pump diodes, and at the end there is just a piece of nonlinear fiber that is also spliced to the output, so there are no free space part. Also dispersion management is everything is all fiber. And if you want to have a shorter wavelength, then a solution, conventional solution is as following: just boost up the power out of the frequency comp, shift the wavelength, and frequency doubled. So here we can see a tuning range of this such a second harmonic unit that we call DFC DVs, design visible. And just by changing the pump current of the oscillator and shifting nonlinear crystal in second harmonic generation unit, one can cover something like 60, 70 nanometers just with one extension. And this is how such a second harmonic generation unit looks like. So this is just output fiber from the amplifier, some collimation optics, focusing optics, nonlinear crystal, collimation and coupling into the fiber. And here maybe you can see this is the size of a connector, fiber connector, so this is pretty small and compact unit. Maybe just a summary. So many comps are very similar. So usually they operate at 1.5 micron or around 1 micron. Repetition rates are around several 10 up to 200, 250 megahertz. And typical width of the comp is something like 25 microns. With extensions, one can just go much broader. And the stability of the frequency comp is given by the reference. So when locking to the RF reference, one gets stability something 10 to the minus 13 in 1 second. And when locking to the optical reference is given by optical reference mainly, and it's something like 10 to the minus 16 at 1 second and going down with a longer integration time. Outputs that are possible, it is obviously around 1.5 micron, around 1 micron with ytterbium comps, and going down to something like 420 nanometer, and on the longer wavelength part, 2.2 microns, or even more with different techniques. This is just brief. I'll just briefly mention. Okay, there are some extensions like that. Beam combining units like this one, and monochromatic detector that I mentioned before. I will talk about it later. So right now I will switch to a little bit different topic. And there are laser systems for industrial and quantum technology applications. And while looking at the company portfolio, one can see that there is a great selection of laser diodes fitting most of the experiments that you are working on. And I will not present right now this part of the talk. You know much better what kind of lasers you need for your experiment. And just I will mention that, the spectral coverage of a frequency comp is a little bit lower than available wavelengths of the laser diodes. But while locking comp to the fundamental wavelength or harmonics, we can lock every TOPTICA laser to our comp. And right now, what I would like to show you is just an example of a laser system for calcium and strontium experiment. And And the laser systems usually looks like this. It starts with frequency comp, some extensions, and a huge number of laser diodes, beat detection units with beam combiners and monochromatic detectors, locking electronics. There is clock laser, including high finesse, cavity, again, locking electronics, PDH lock, wave meter with some switch, control software, frequency counters, or spectrum analyzers. So we can see that there is a pretty complex experiment, and you know it very well from your labs. It occupies maybe one optical table. And we are happy, we have everything, but this is not what industry would like to have. They want to have a system with hands-off operation. They want to have a system with a higher reliability. They want to have a system that operates in a harsh environment, but in the case of quantum experiment, harsh could mean that it's not on the optical table, but just next to it. Industry would like to have complete solution. So not just a number of lasers, frequency comp, beat detection units, and locking electronics standing next to each other. They want to have yeah, so they want to have everything, and they want to have that it's integrated into one system with a common interface. And that is what we are working on. And I would like to show you some results as a very short presentations of the projects that we are working on. So the first project that I would like to show you is OptiClock project. And this is a project of several universities, companies, and institutes inside of, so within Germany. So it's a PTB, and Ferdinand Braun Institute is delivering a diode for a clock laser, yeah, 2 universities and the companies. So project started in May 2017. The main duration is of 3 years, so the project will finish in May next year. Overall budget was 6 million euros and 4.4 million of public funding. The rest was a contribution from industrial partners. 2 coordinators, one is Jürgen Stuller from TOPTICA and Pete Schmidt of PTB. So what are the goals of OptiClock projects? It's a development of an optical single ion clock as a foundation for product development. So that was required for by a German government, that there is industry behind. So that should be an Ytterbium ion clock. The maximum size would be 2 19-inch racks. It was required that that clock operates long term and stable operation. It should be operable by non-specialists, so it should be so easy to operate that one do not need any PhD in physics in order to control it. And there should be also some user-friendly control interface. And the benchmark was that the stability stability of the clock should be at least 10 times better than commercial hydrogen maser. And one very big objective was technology transfer from research institutes to industry in order to support or make a push for the quantum technology sector in Germany. So here, this is a picture of a clock laser laboratory at the PTB, and we just want to shrink everything into 2 19-inch racks. And the mass should be less than 1,000 kilograms, power consumption is less than 3.6 watt, and the dimension was limited by a size of typical door that one can still shift it. What are the technological challenges? So obviously, there is a lot of engineering involved, and that was an integration of extremely complex system into just 2 19-inch cabinets. So a number of modules and subcomponents had to be redesigned. Very big issue is a heat management. So there are just these are so all the electronics and optics that just occupied a great volume of on the optical table or over and under optical table is right now concentrated in smaller volume. So there is heat management is obvious issue. Protection against external perturbation of any kind, electrical, magnetic, thermal, acoustic. Obviously, such a rack is not optical table, so vibration can be issue. And okay, there are several industrial partners, several components. So of course, interfaces between products of different companies need to be redesigned. And one of the objectives was transportability, to have plug-and-play system, so it should be possible to move a system from one laboratory to another. And another point of the wish list, should be automated operation and troubleshooting. So this is an overview or the concept. So there is ytterbium ion trap, laser part, and switching boxes of TOPTICA. The whole physics package came from PTB together with University Siegen. 1 Hz cavity comes from Menlo, and the laser for a clock laser for Ferdinand Braun Institute. And this is how the, so this is right now in overview, who is responsible for what. We as a TOPTICA, we are responsible for the laser system. It's not a tabletop laser anymore, it's a laser system that is rack mountable. And we are responsible together with PTB and Cubic for the switching box. We are also responsible for the whole clock integration. So our coworker works very often at the PTB. High Finesse provide a rack mountable wave meter. Physics package, it was PTB, University of Siegen, and company Wacom. Clock laser that at the time of, so right now the clock laser is still not available. So this is Ferdinand Braun Institute, Wacom, and Menlo Systems. And control hardware, it's a PTB together with Quartec. Yeah. And the location of integration, it was chosen to integrate the clock at the PTB as a neutral ground. So not that TOPTICA complains that the integration takes place at Menlo, and Menlo complains about integration at TOPTICA. So we decided to have a neutral institute. And this is how the system looks like. So at the end, the cabinets will be behind the doors. And current status after 2/3 of the project duration. So there is an ion trap, it's already operating. And actually the whole clock is already operating by utilizing clock laser from the PTB. And we can see the very nice results. So this is the red one, is performance of the hydrogen maser. This is the performance of 2 ytterbium clocks at the PTB, and the black one is the performance of the OptiClock. So obviously it's a little bit worse than 2 Optical clocks that are located on optical tables, but that is also what we expected. But it's not much worse, and it's 10 times better than hydrogen maser, so we are pretty happy with the results. And right now in progress, it's autonomous operation, and the next step will be integration together with a clock laser that will be available very soon, and evaluation of the clock. And what we're gonna do, or what happens next. And so the goal is that the components of that OptiClock will be available on the market. So the whole laser systems, so we are already there, light distribution, switching box, control electronics, and software for quantum experiments, and ion traps, including vacuum technology. Another goal was to establish long-term business partnership with other companies to just boost a little bit quantum industry in Germany. We are thinking about commercialization of the system, create jobs, and maybe for metrologists, the more important is that such a clocks contribute to international atomic time. The next project that we have is integrated quantum clock, iqClock. There are most of you are from the consortium, so I will just limit myself. So I will limit this talk only to the part that TOPTICA is involved, and this is industrial part of the consortium. In that industrial part, We have several companies. We are responsible for a laser system. Actar is responsible for a very black coating inside of the physics package. Teledyne E2V is responsible for vacuum system and physics package. NKT for fiber delivery. University of Birmingham is responsible for system integration, and there are two end users. One is Kronos, so this is a company that manufactures time distribution systems for British Telecom, and British Telecom will be the end user that will benchmark our system in one of the in one part of the telecommunication network. So our part is the laser system for strontium lattice together with a clock laser. So we took one more work package and together with a frequency comp. In the OptiClock system there is no frequency comp, so there is no transfer down to microwave. And the system looks like this. So we decided to get rid of second harmonic generation system. So we just use two conventional DR Pro diode lasers at 649 for blue mode. 707 and 679, these are repumpers. And second mode stage 682, these are also conventional lasers. So this is that MDL. These are the rack mountable laser diodes engine that we've seen in OptiClock project. The new thing is MTA. So it's a rack mountable tempered amplifier. This has to be developed inside of the within the project, and also rack mounted frequency comp with all the extensions needed to lock the lasers to the comp. And a clock laser that is also supposed to operate inside of the rack. And the clock laser is conventional ULE spacer of PTB design. We are right now currently at the process of technology transfer. Yeah, so what we can see is a test bed. So we need to guarantee that all the components, laser diodes, electronics, frequency comp, bit detection, that everything works in a rack. So we've built a test bed, and what you can see here, wave meters and all the stuff. And we just put it next to the setup, just on the conventional optical table. Here in the back, we can see conventional, commercially available cavities at 1162. Our design will be much smaller and fit inside of the rack. And so one objective of the system is to prove that we can lock inside, so we can lock the laser diodes to the comp within, inside of the rack, and that we can guarantee the operation, that frequency comp is still operating good enough to, in order to perform in optical clock system. So the first step was just frequency comp, so comp comparison, two comps, one of them in rack and the second on the optical table, and lock to the common RF reference. In this case, it was rubidium clock, and one comp as a master. There is a laser diode at 1.5 micron locked to the comp over phase frequency detector and PID Falk, and beam from the laser is guided to the second comp on the table, and beat signal is measured by the counter. So this is out of loop part of the signal, and this is in loop part. And the stability or instability measurement shows that in this case overlapping Alan deviation is at 1 second, something like 2 × 10⁻⁴. That is pretty good value. and it continues to average down to 10 to the minus 18 level. So it is very fine, but in optical clock operation, we need to test the performance with optical lock. So in this case, RF reference was replaced with 1 Hz cavity, and the same story. Both of the comps were locked to the cavity, and the laser diode to comp number 1, and the bit was performed in comp number 2. And in this case, we performed that experiment twice. Once was the one comp was on the optical table, and the second comp was in the rack. In the second experiment, we just moved both of the comps to the optical table to see what's the performance in a proper lab environment. And this is what we get. The black one is just Allen deviation of the 2 comps on the optical table. So as good as we can measure is up to 10 to the minus 19. Not as good as the PDB measurements, but very decent values. And the red one is a measurement with 1 comp in the rack. So at least to the level of something like 10 to the minus 19, we cannot see any difference between comp operation in a rack and optical table. So this red measurement was done as a first one, so that is why we just finished the measurement after 10,000 seconds averaging time, and when we performed the measurement with both comps on the optical table, we just saw, oh, this is the same value, let's measure a little bit longer, so that is why these measurements are not of equal length. And the next project that I will just very briefly mention is iqClock. So this is another European quantum flagship project together with ETH Zurich, Atos company, Oxford University, Fraunhofer, University of Innsbruck is a central part, and much more universities and companies. And the goal of iqClock is advanced quantum computing with trapped ions. So we are not only interested in optical clocks, but there is also much bigger market behind that, like quantum computing, quantum simulations, and quantum telecommunications. And so this pictures comes from coordinator of the project, University of Innsbruck. So this is a typical environment or how the experiment looks like. And what we're gonna do is again to shrink everything into 3 19-inch cabinets. And the goal is to have a scalable 50-qubit quantum computer based on industrial standards. I will not talk much more about it. This project is somehow related to Pasquans that we also have in TOPTICA, so this is quantum simulation. And in any of these projects, we're responsible for the laser systems for the quantum experiments, and all of them are supposed to be in an industrial standard rack. And we have few minutes. I'm afraid that there is unfortunately no sound, but we made a small commercial that shows how frequency comp behaves when it's optically locked to the optical reference and when we do nasty things to the comp and regular work in a day, like screaming and arguing in the lab, or here we can see the sound pressure. So there was a fire alarm in the lab, and we had to leave, and the comp stayed locked. There was some football game, soccer game, and a goal, and that very high noise and pressure seems to be okay for the comp. So at the night we had some party. At night is of course there is a cleaning in the lab. It doesn't matter, laser stays locked. At the very night there is a party. So we misuse the comp and as a drum set, and it seems to be okay. So the technology is pretty mature, and yeah, and so this is maybe not a lot of science as you do. This is a lot of engineering, a lot of work to make the products reliable and good enough for industry. So this is just a transfer. So that was really a full comp system. This is just one small box. So everything that what is needed is within that blue box. All the electronics, everything. And this is unpacking at the iCap trade show in Barcelona. Installation time. And after 1 hour, laser is locked to the optical reference. And still operating the whole day at the trade show. Coming back home and yeah. So that is what I wanted to show you. So yeah, there is interest. Industry, so there is a lot of industry that shows interest in quantum technology, not only optical clocks, but quantum computing seems to be also very important. And together with you as a university partners, we try to develop the mature technology to deliver solutions to the customers. Thank you.